All right, guys, today we're going to start taking a look at the remainder and the factor theorems and how they apply in our little journey towards solving higher order polynomial equations. So first, we'll get started off with a little warm-up. So we have two different division problems where we want you to go and use synthetic division. So I'll give you guys a minute to work on those, and we'll go over them in just a sec. All right, now that you've had a chance to go through and work on all of those, let's go through and make sure that we did everything correctly together. So in the first one, we had x cubed minus 2x squared minus 2x plus 8 divided by x minus 1. I should tell that if this is my factor, then x equals positive 1 would be the solution or the root or the 0. So I'm going to use that when I'm doing synthetic division. So I see that I have exponents of 3, 2, 1, none. So everything's in order, and I can just put the coefficients of 1, -2, -2, and positive 8. Going through the process of using synthetic division, copy down that first term. 1 times 1 is 1, -2 plus 1 is -1, 1 and -1 is -1, -2 and -1 gives me -3, 1 times -3 is -3, so I'm going to end up with a remainder of 5. Okay, but what does it mean that I get when I divide this polynomial by this binomial? It means that the quotient is 1x squared minus 1x minus 3, and then I'm going to have a remainder of 5 over my divisor of x minus 1. Okay, let's go take a look at the second one. Second one, we've got x cubed minus x squared minus 2x plus 8, and we're dividing that by x plus 2. So first I should realize that if this is my factor, then the solution that's going to come from that is -2. So I'm going to use -2 as my synthetic divisor over here, and I'm going to check 3, 2, 1, none for my exponents. So it is written in standard form. Let's just get those coefficients. 1, -1, -2, and 8. Remainder over here. Copy down that very first term, 1, and then start multiplying in waves and add those columns. -2 times 1 is -2. -1 minus 2 is -3. -2 times -3 is positive 6. -2 and 6 will give you 4. And -2 and 4 will give you -8. Aha, so this one, we have a remainder of 0. Because we have a remainder of 0, we should be able to tell that x plus 2 is actually a factor of this particular cubic polynomial. The other factor would end up being 1x squared minus 3x plus 4. Okay? So this is really serving as kind of our introduction to the remainder and the factor theorems. Okay, so we see here one example. We had a higher order polynomial. We did some division. We were able to use synthetic division, and we saw that it had a remainder. So it's not evenly divisible, so it's not a factor. But over in the second one, when we did our synthetic division, we found it did have a remainder of 0, which tells us that it is a factor. And because it is a factor, that can be a really useful tool moving forward. So in class, we've talked a lot about what the factor and remainder theorem are, but we haven't explicitly defined them. So let's go ahead and do that now. So first off, we have what is called the remainder theorem. Okay, the remainder theorem just states that if some polynomial, which we generically call f of x, is divided by x minus k, then the remainder is whatever f of k is. Okay, so we can also go through and use synthetic division to do what's called synthetic substitution, because what we're actually doing is we're actually evaluating the function at that point. Okay, so if we were to go back and take a look at our warm-up problems, if you were to go through and plug the number 1 in warm-up problem A into the problem, do you know what you would get as a value of f of 1? You'd get 5. 1 cubed is 1, 1 squared is 1, 1 to the first is 1, so this is really just 1 minus 2 plus 8, okay? You're going to end up with 5. Over here, if we go and we plug in a negative 2 in for all of these x's, well, negative 2 cubed is negative 8 minus 4 plus 4 plus 8. Notice all of those are opposite signs, so they all just wipe each other out, and you're left with f of negative 2 equals 0. So when we look at the remainder theorem, it's basically just telling us that we can use synthetic division or also substitution to evaluate a function at that point, okay? So why is that important? Because we can also then use the factor theorem, okay? The factor theorem says that if f of k equals 0, then f of x has a factor at x minus k. So when we're going and doing the synthetic division or substitution, and we get a remainder of 0, it's telling us that we have a factor. And that's important because that's going to be the first step that we're going to be taking towards being able to solve higher order polynomials. But before we solve them, we need to break them down into pieces that are solvable, which means we're going to have to start factoring them. Okay, so the focus of today is taking a look at a larger polynomial, a cubic or a quartic polynomial, and we're going to be using the remainder and the factor theorem and some given information to try and factor that large polynomial into as small and as many of small pieces as we possibly can. So let's go take a look at example 1 over here. All right, in example 1, it says factor f of x equals 3x cubed plus 13x squared plus 2x minus 8, given that x plus 4 is a factor, okay? So ultimately, we're trying to write this as a series of smaller polynomials that are all multiplied together. We know that one of those is going to be x plus 4. So what I need to do is, if I'm trying to go through and factor all of this, I need to go and do some synthetic substitution or division. What would I be using as my synthetic divisor in this case? Well, if x plus 4 was set equal to 0, then its solution would be negative 4. So I'm going to go and do some synthetic division using negative 4. Checking my polynomial, the exponents are 3, 2, 1, none, so it's in standard form. So I've got a 3, a 13, a 2, and a negative 8. And again, those come from 3, 13, 2, and negative 8. But before I get started actually doing the work, I know that this has to be a 0. I know this has to be a 0 because I've been told that it is a factor. And if we go back and look at the factor and remainder theorem, it says if f of k equals 0, then x minus k is a factor, okay? So it's got to be a 0 there, all right? If I don't get a 0, I might have made an algebraic or arithmetic mistake somewhere in my process and might need to go back and check it. All right, but let's see if we do get 0. So take the 3 and copy it down. Negative 4 times 3 is negative 12. 13 minus 12 is 1. Negative 4 and 1 is negative 4. 2 minus 4 is negative 2. And then negative 4 times negative 2 is positive 8. So I do, in fact, end up with this. But what this tells me is that I can actually go and write this in a almost or more factored form as x plus 4, and I know that's a factor because that part was given, but then I also have a 3x squared plus x minus 2, okay? So this is a more factored version, all right? But could I go and factor more? Well, x plus 4, that's a linear binomial. I can't really factor that. But this quadratic trinomial, could I factor that more? Possibly. It has a leading coefficient, so that tells me that if it's factorable, I'm probably going to need to use split the middle. So I can take the 3 and the negative 2, multiply them together and get negative 6. Are there any factors of negative 6 that will add up to a positive 1? And we should be thinking about 3 and negative 2. So we can rewrite this function here as 3x squared plus, I'll try and keep the colors the same, plus 3x minus 2x, that's the part where we split the middle, and then minus 2. So now I can go and do my factoring by grouping, right? Okay, so I can take out a 3x over here, and what's left is x plus 1. What can I take over here? Well, the first sign is negative, so I'm going to take out a negative 2. And what's left? Well, x plus 1. So do those matchy-matchy? You bet your sweet bippy they do. So what's my final answer going to be in total factored form? My original known factor of x plus 4, followed by what I just found from factoring this quadratic trinomial, where I can see that one of the factors is going to be 3x minus 2, and the other one is this x plus 1. Okay, so this has now been written out in totally factored form. There's nothing else I can do to factor this any further. There's no GCFs, there's no factorable quadratics. These are all nice, pretty linear factors, okay? Which means tomorrow when we start talking about solving, it's going to be real easy to solve this, okay? So let's go take a look at another one. This one says 1, 0 of f of x equals x cubed plus 6x squared plus 3x minus 10 is x equals negative 5. Completely factor the function. Okay, so they've given me a 0, but can I use the remainder in the factor theorems to turn that into a factor? Sure. If I know that 1, 0 is x plus 5, that means that it must have a factor, or sorry, that x equals negative 5. It must have a factor of x plus 5, okay? So if I'm going to completely factor it, I probably need to start doing some division, all right? So let's go through and take a look at this x equals negative 5 and do some synthetic division. When I check my polynomial, I have exponents of 3, 2, 1, and none, so it is written in standard form. It does not have any skipped powers, so I can just put down the coefficients of 1, 6, 3, and negative 10. And I already know factually I should get a remainder of 0 because I've been told that a 0 of this function is negative 5. So when I plug in negative 5, I get out a 0. So let's go through and confirm that. So if I copy down the first term, negative 5 times 1 is negative 5. 6 minus 5 is 1. Negative 5 times 1 is negative 5. 3 plus negative 5 is negative 2. Negative 5 times negative 2 is a positive 10. That is a remainder of 0, so I'm well on my way to completely factoring. I can use my first factor that I wasn't exactly given, but I'm smart enough to figure out that that's exactly what it is. So I have x plus 5, and then I also have x squared plus x minus 2. Okay? So why is it x squared plus x minus 2? Well, 1x squared, 1x, and minus 2, remainder of 0. Okay, so if I look at this one, is there a way that I could go and factor the green quadratic trinomial anymore? Well, are there any factors of negative 2 that add up to positive 1? Well, sure, 2 and negative 1. So I'm probably going to keep my factor of x plus 5 over here, but this is now going to be factored into x plus 2 times x minus 1, okay? Since factors of x squared are x and x, so x times x is x squared, x times negative 1 is negative x, plus 2x is plus 1x, so that does give us our middle term, and then our constant of negative 2, you do get if you multiply positive 2 and negative 1 together. So the completely factored version of this is right here, okay? So again, we're kind of using a combination of the factor and the remainder theorem to identify some given factors, use synthetic division or substitution to factor out these polynomials or factor down these polynomials. And tomorrow that's going to come to a head when we start going through and actually solving them, okay? So let's take a look at one more problem. Example 3 says one factor of f of x equals 5x cubed minus 27x squared minus 17x minus 6 is x minus 6. Find the other factors of the function. Okay, so again, I know that if x minus 6 is a factor, then it's got to have a solution where x equals 6, which means I can evaluate the function at 6, and I will get 0 as my remainder, which is also me dividing the function, therefore factoring it out. Okay, so let's put the coefficients because this is all in standard form already. So we have 5, negative 27, negative 17, and negative 6. I already know I should get a remainder of 0 because it said it's a factor. So doing my synthetic division, take that first number, just copy it right on down there. 6 times 5 is 30. Negative 27 and 30 gives you 3. 6 times 3 is 18. Negative 17 plus 18 is 1. And 6 times 1 is 6. So I do, in fact, get a remainder of 0. All right. So what I have is when I'm writing it in factored form, I have my original x minus 6, which was given, and then I have the piece that I just found. Okay. Because remember, dividing is really the same thing as factoring. So when I divided this by x minus 6, I ended up with 5x squared plus 3x plus 1. So just like in the other problems, I've now taken the cubic function and I've factored it down into a linear factor and a quadratic factor. So can I factor the quadratic any further? Well, it's a quadratic trinomial with a leading coefficient that's greater than 1. So if it is factorable, maybe I can factor it by split the middle. So 5 times 1 is 5. Are there any factors of positive 5 that will add up to 3? And the more you think about it, the more you realize it's just 1 and 5. 1 and 5 will never make 3. So this is actually not factorable anymore. Okay, which is kind of sad, but at the same point, it's kind of nice because guess what? If we can't factor it anymore, then we've totally factored it. We've also identified what any other factors could be. All right. So sometimes when you factor, you can keep factoring. Other times when you factor, you get to a certain point and you can't really factor any further than that. Okay. The good news is, not that you need it for today, but you do have a method that you can use to solve any quadratic, whether it's factorable or not. It's a very famous method. There's songs that are sung about it in algebra classrooms across the world. But we'll get to that tomorrow. For today, we're just focused on factoring, so we're all done here. Okay, so to recap what's going on, okay, we have these two theorems, the remainder theorem and the factor theorem. The remainder theorem says that if you divide a polynomial by x minus k, the remainder is f of k, essentially the same as evaluating the function at the solution for that particular binomial. The factor theorem tells us that if f of k equals 0, then f of x has a factor at x minus k. So you'll see the remainder and the factor theorem kind of need each other to really exist. What we've done is in each one of these cases, we've been given a larger polynomial and asked to factor it. Our older methods that we would have used to do that, like factoring by grouping, don't work. So we need to use division as a method of factoring. By using division, we're using the remainder theorem. By identifying this as a 0, we've got the factor theorem. Once we've gone through and begun factoring, it may be possible to factor it even more based off of what factors emerge in our factorization process. Sometimes we have quadratics with leading coefficients that we can factor further. Sometimes we have quadratics that don't have leading coefficients that we can still continue to factor more. And sometimes we end up doing one a little bit of factoring and we're kind of stuck at that point. We can't factor anymore, but that's okay because we've been able to go and rewrite all of these polynomials in their fully factored form.